Hi, welcome to another edition of Linear Algebra. Today we are going to talk about distance between points, lines, and planes. So we talked about the idea of a distance in the context of distance formula from college algebra, and that was extended to 3-dimension. So if we have 2 points in space, let's call them A and B, then the distance of A from B was the length of the vector, so B minus A or A minus B, and that was given by the Pythagorean formula, which asks us to subtract the x's, subtract the y's, and subtract the z's, square each, add up, and take square root. So we want to go a bit beyond that. The general idea is that if you have two shapes, when you talk about the distance between them, you are actually talking about the shortest distance. Okay, so when we're talking about distance, that's what we mean. Of course, this is in an idealized environment where there are no obstacles and you're just in a flat field. You can go from any point to any other point. What we want to do is to ask the question, what if I have a point and a line? What's the distance between the two of them? And of course, again, we mean the shortest distance, and that of course means it's going to be the line that connects these two is going to be perpendicular to the second shape. That is in fact true for any kind of shape. It doesn't have to be flat. That's always the case. Next problem we are going to look at is, well, what if I have a plane and a point outside, and the question is, what is the distance? Of course, if it was on the plane, the distance would be 0, but now we have an arbitrary point outside. We can consider this problem in two cases, either in R2 or in R3. Going beyond these two problems, we could have a plane and a line, and we could ask about the distance. Of course, if the plane and the line were intersecting each other, the shortest distance would be 0. So the only case of interest would be when the line is parallel to the plane, and in that case, any point that you pick on the line will give you the same answer, as in if I find the distance here will be same answer as if I find the distance somewhere else. It's all the same distance. So this case will be reduced to that easily. There's nothing to be done. Similarly, if you have two planes, well, if they are intersecting each other, well, the distance will be 0. The only case that's going to be non-trivial is what if they are parallel to each other. And again, you just consider a point here, and the distance of it from the second plane will be the distance of these two planes. Going a little bit further and deeper, well, what if I have two lines? Again, if I have the two lines intersecting with each other, well, the shortest distance between them will be 0. If they are parallel to each other, again, if you choose any point here, the distance from the other line would be what you're after, and you're all set. Let me ask you a question. Is that all there is to consider? If you consider two lines, is it always the case that they are either intersecting or they are parallel? is there a third case? So think about it for a second. If I have two lines, other than intersecting or being parallel, what's the third option? Did you figure that out? Well, there's a third option, which is sometimes referred to as a skew lines. Skew lines are two lines that, well, of course, they neither intersect nor are they parallel. Easiest way to think about it is, well, you think, look at the room around yourself. Your room looks like a box. I'm sure it looks a lot nicer than a box, but it's actually a box. Now, on that box, if you look at, say, this line and then this one, they are obviously not parallel to each other, and they do not intersect either. So that's a case of interest. In that case, you will say the distance is just the height of my room. Well, what if the lines were not the edges of a box? The problem is still there. You can hold two sticks in the air and hold them in a position that they do not intersect and they are not parallel to each other. You will see what the question is. Where would be the shortest distance or shortest bridge between the two of them? I'm going to leave that problem to you as a kind of additional one of those lanyard problems. If you're interested, you let me know. Let's go after the rest of them. So where shall we start? Perhaps I'll start with this case. Distance of a point from a plane. Distance of a point from a line in R2 will be almost identical to that. Distance of a point from a line in R3. Well, that's going to be a bit different from the way it is in R2, so we're going to do that. A second set of problems that are typically mentioned right next to these is, well, you are always dropping this perpendicular. Tell me, where is this other point? Or here, where is this other point? So sometimes the question says a point is given outside. So I have a point outside here. The question is, what point on this line is closest to that? Let's call it something like H. Find that point. Again, a point outside might be given here, and the question is, what point on this plane is closest to that? That will be H. Of course, a simple example of that is what you do during making plumb lines to a floor. So if you have a floor, which in this case of course is going to be horizontal, and you have a point here, if you take a heavy object and attach it to a line and let it drop here, you call that of course the plumb line, and the point that it hits the floor would be the H for you. That is nearly a trivial case, mathematically speaking, in terms of finding where this location of this point is going to be if you have the location of that point. If you have x, y, z here, well, x and y here is going to give you the answer on your xy coordinate plane. But if your plane is at an angle or something, the problem is going to be more interesting, and that's what we want to do. Okay, there are several ways of doing this problem. Some of it you might have even seen in high school or pre-calculus classes and such. Let me remind you, solving this problem in R2 is a standard problem in college algebra or pre-calculus. So in that case, you are still in two dimensions. So we are here, we have some line is given to us, some point is given to us, and the question is, what's the distance of this point from this line? So again, simplifying assumption, you are in two dimension. So the way you would have done this problem in high school would have been to find the slope of this line, find the negative reciprocal of that, so that it will give you the slope of the perpendicular line. So now you have a perpendicular line. So if the slope here was so-called m1, then the slope of this one would have been -1 over m1 because it's perpendicular. You find the equation of this line, find the intersection with the other one. Once you have the intersection, you actually have your h first, and then you find the distance of these 2 points by the distance formula, and then you'll have your distance. Okay, so the problem is not new at all. It's some basic problem. The nice thing in linear algebra is that we can do this thing in a very concise way, simple formulas, clean cut and general. And also we are going to see some of the application of some of the ideas we have worked on. Well, what were the main ideas we had so far? We had the projection formula and questions of anything perpendicular ties in with that projection formula. So let me remind you what we have shown in the previous lectures, so that we start from there. So that was the preliminary discussion, preliminary discussion on as to sorry. So you remember that if I have a vector, let's call it B, and another vector, call it A, both of them starting at the same point, I can resolve A along B and the perpendicular to B. So this would be the projection if I go directly. So let's call this thing P, and let's call this one, let's color it differently. And I will have N. So what was the formula for P? P was A dot B over B dot B times B. And length of P, to make it nice and simple, it was A dot B, and in the denominator was the length of B. Let me remind you again, I am using single vertical bars for both absolute value and the length of a vector. So in your textbook this is going to look like this. It's just that there's so many bars to write. Okay, and then how about N? Several formulas for N. To get started, simplest thing you can write is A minus P. That's just what N is. And then you can also talk about this angle and use the sine and cosine of that angle. Okay, with that in mind, let's go ahead and without further ado find the distance of a point from a plane. So I have a point here. Let's call this thing point P. Point P is gonna be a vector with 3 coordinates. Let me write them A, B, C. Now this A, B, C has nothing to do with those A and B over there. It's just 3 numbers. The equation of the plane. Let's just write something like ax plus by plus cz is equal to d. That's the equation of the plane. So we want to find the distance of this from that. So standard question would be find distance of P. Let's call it, say, 2, 3, 4 from let's say 5x plus 6y 7z is equal to, say, 10. So that's the idea. Okay, again, we can approach this problem the way we have done it in high school, by drawing the perpendicular line, finding intersection, finding distance, and so on and so forth. So that's definitely possible. It's going to be a little bit lengthy. But now, so let's remember where the equation of line came from. Let's see if we can use that. There are projection formulas to get the answer quickly, so that we can answer this in a matter of a minute. So to find the equation of a line, you remember the main idea was that you needed a normal vector to it. So normal vector of this plane, you remember, was just the coefficients of a, b, c of the equation itself. And if you had some point on the plane, let's call this r0, and some other point, let's call this thing r. So r0 was some point on the plane, like x0, y0, z0. R was some general points roaming around all over the place, x, y, z. The equation of plane was that, well, the line from r0 to r should be perpendicular to n. So our equation really was r minus r0, which is exactly this vector, is perpendicular to n. So if you dot them, you do get 0. In other words, r dot n was r0 dot n. So r would be x, y, z, n would be a, b, c, and r0 dot n will be, well, if you want to write it, x0, y0, z0 dotted with the same a, b, c, and this thing is supposed to be on my right hand side, so this is just d. Okay, let's do the following. I'm gonna take this point P, connect it to my R0. So P is outside, R0 is on the plane, and I copy N here, and then I find the projection of P on this vector. So projection of R0P on N is going to have what kind of a height? What's the significance of the length of this projection? Let me again ask you to think about it for a second. If I take P R0, project it on this vector N, what would be significance of the length of that projection? Think about it for a second again. So this is our clue that you take a look at some nice picture and think deep in thought as to, well, what is this? Why are we talking about that? What's the significance of that? Did you figure it out? Let me give you a clue. Well, what if I go directly down here? That blue and that yellow are the same thing. What is the significance of the blue? Of course, the significance is that this is perpendicular that is exactly the distance we are looking for. So length of projection of r0p on n is same as distance of point P from the plane. Well, how do you find length of a projection? You take the vector, dot it with your vector that you are projecting on, divide by the length of that. So what I have to do to find this is I take r0p, this vector, dot it with n, okay, dot it with n according to this formula, dot it with n, find the absolute value of that, divide by the length of n. So the length of n is this length of n. That's what we have to do. Okay, what is r0p? r0p, a vector going from any point to any other point, is equal to the difference of the two endpoints. So that's going to be p minus r0 dotted with n divided by the length of n. Numerator, this is a number. To convert it to something positive, we are taking an absolute value of it. Well, let's multiply. So this becomes p dotted with n minus r0 dotted with n. I realize some of you might be kind of feeling uncomfortable with some calculation that doesn't have always numbers in it, but you have to push yourself to elevate yourself from that arithmetic orientation that you see here to more higher level, which is algebra orientation. This is exactly what you would have done with these numbers, but you have to concentrate, push yourself, bring yourself to a higher level to follow the algebra as opposed to being tied down to arithmetic all the time. Okay, so this is what I want to calculate. Well, what is p dot n? Remember, p was some point outside with coordinates a, b, c, something just like here, 2, 3, 4. N was normal to the plane. Normal, you extract it from the equation, which in this case like 5, 6, 7, or in general we just wrote it a, b, c. So let me write a, b, c. So the example, let me clean this up. Sorry. So the point that we are given in example is 2, 3, 4. The plane that we are given is 5, 6, 7. So when I multiply p and n, what do I get? A times a, b times b, c times c. So I'll have a times a, b times b, c times c. So this, and this one. Minus r0 times n. r0 times n, we said that's the d of the right hand side, whatever that d is. So minus d. This could be positive or negative, so we put it in absolute value. Divided by the length of n. Well, how do you get the length of something? That was the Pythagorean formula in 3 dimensions. So I will write it. A squared plus b squared plus c squared. So this is the distance. This is a distance formula. Actually, this is one of the exercises in this section. You might think that, well, I did the exercise for you. That's the distance. So if the question was, what's the distance of this point from this plane, the point is given by three numbers. The plane, something times x, something times y, something times z equals to some number on that side. So what we do is to multiply these three numbers with these three numbers, subtract the right hand side, take the absolute value of that, and then these three numbers for the plane, square, add up, take square root, divide the two entries. So what did we say we do? So our ABC is 2, 3, 4. So 2, 3, and 4. They have to be multiplied by little ABC, 5, 6, and 7. 5, 6, 7. Who's D? D is the number on the right hand side of our equation for the plane. So minus 10 divided by the length of the normal vector, little ABC. So who is that? That's from the plane, 5, 6, 7. So I have to square them. 5 squared, 6 squared, plus 7 squared. That's what the distance is. So all that's left, basic arithmetic. So 10, 18, 28 minus 10. Let me make sure that this is not confused with anything else. 5 squared, 6 squared, plus 7 squared. So this happens to cancel. 30, 46. It was positive, so I dropped the absolute value and the denominator. So let's write it 25 and 36. And then I have 49. So this is 22 and it looks like 110. So here's our distance formula. It came out without that much work and effort, substantially less work than what we said would have been done in high school. Say in high school you have to draw or find out the perpendicular line, find the intersection, find the distance apply the distance formula for these 2 points. That would have been quite substantial. What we have here is a much shorter way. Well, let's also say distance of a point. So I'm now gonna specialize in R2. If I have a problem from high school, I have a line here and I have a point here. So I have a point P, coordinates A and B, and I have a line here. Let's say equation of it is ax plus by is equal to d. So I put the d here so it looks like this. What's the distance of this from that? Instead of all that work in high school, distance of point P with coordinates A, B from line ax plus by is equal to d is, it's exactly the same as this, just you don't have the third component, is a copy of this, a b minus d, over radical a squared plus b squared. Okay, so let's keep the videos short so that you do one item at a time. What we have done here, let's see, we have done the case of R2. In case of this one, we didn't find the point H, we found the distance. Okay, you want to do a few exercises related to that, and then we are going to continue the next lecture from where we left off here. Until the next lecture, good luck and God bless.